scope in our presentation is addressing an approach to improve the accuracy and reliability of pulse oximeters in measuring oxygen saturation levels in racially diverse populations. So our motivation, pulse oximeters are critical for monitoring SpO2 values in patients with COPD. Over 16 million adults in the US are affected by CPD alone, and accurate SpO2 readings allow early detection of hypoxia, which is vital for preventing complications and guiding treatment. Conventional oximeters rely on red and infrared wavelengths, which can be inaccurate for individuals with darker skin tones. During the pandemic, about a 4 to 7% error was read in patients with higher melanin levels. Target market and potential users. Primary users are COPD patients, elderly individuals, patients in home care and telehealth settings. Secondary users are first responders, rural health workers, and sleep disorder clinics. So our functional requirements, we want reliable SpO2 readings, plus or minus 2% accuracy, real-time data processing, and battery efficiency. For physical requirements, we want it to be small and lightweight, have a clear display, and have a good rugged construction. So these are our standards that go over our testing, battery performance, biocompatibility. It's a Class 2 medical device and requires a 510K. So our engineering constraints are just that our accuracy needs to be close to FDA-approved devices. Our response time needs to be fast enough to alert users in real time. It must be small and comfortable, and our costing each rate is $700.
Okay, so for our design approach, we're looking for calculating SpO2 using modified Beer-Lambert's law, which we made some adjustment for it, since we're going to be for our device we're going to be using 2 detectors and 3 light source, so we had to do further modification for the equation so it can read for 2 detectors, not 1. And initially we chose 3 wavelengths, which is 470, 555 and 590. The reason that we chose these wavelengths is because where the 470 is a short wavelength, which we will be accounting for melanin correction, and the 555 and 595 wavelength, we chose it because it has we can distinguish between HPO and HP, so it will help us to accurately calculate SpO2 and eliminating the effect of melanin.
Okay. So last semester we initially only wanted to account for 2 wavelengths. With the increase or jump to 3 wavelengths and 2 detectors, our design did have to change a bit to account for the extra space that we needed. This also put a pause on our PCB design, so it is a little bit more messy than we thought it would be. This is our new design. The only 2 things that we had to print were the holder to hold all the probing compartments, that would be the LEDs, and the detectors. You see that here. And then this is a shroud to limit the ambient light. If you look at the picture here, you can see this is the holder and this would be the shroud, and we have a display right there. With our circuit, we weren't able to shrink it down, just because we had to account for the extra wavelength and the detector, so it is about double the size. And these are some tests that we proposed to test our device. This would be testing the SpO2 precision and linearity, testing the inclusivity across skin tones, the response time, power efficiency, and durability. So these are some of our outcomes right here. With our real-time data processing, we were able to get the processing time down to about 2 seconds on average. We could have, regarding our accuracy, we saw that even with double the wait times, or with the LEDs being on or in between the readings, the accuracy didn't change too much, so we found a good balance there. Regarding the battery efficiency, we just charged it and then we let it run as long as we could. On average, it was about 8 hours and 10 minutes. We ran about 10 trials there. So with our drop test, we weren't able to properly test that with our physical device. However, I did run some simulations on SolidWorks with 3 different orientations. Everything came out pretty great there. The max stress came out to about lower than ideal for a medical device, but as it only gives a safety factor of 1.3 to 1.9, the max displacement was acceptable for maintaining the component alignments, and the max frame was about 0.98%, which is just under the 1% target for ABS plastic.
So we have ran a few tests using MCX software. Oh, do I admit?
Yes.
So we have ran a few tests using MCX software. Since we had a few issues calculating SpO2 using Beer-Lambert's law, because it's a very complicated formula and we need to account for so many things, and also we might need to calibrate it. I don't know yet, we're not there yet. So we've used the traditional way to calculate SpO2 using reflectance mode. So we had to plot the ratio of ratios for each OD, and we had to find the best or the most linear ratio of ratio, and from there we can we have ran it across different skin tone. So that's why we have a different best wavelength for each skin tone. The light one, this is the best wavelength only for the light skin tone, which is a melanin fraction of less than 5%. Moderate is from 5 to 10%. Dark is from until up to 15%. I did calibrate the equation, and this is our test results. We have calibrated the equation, and we have actually solved it across. We have actually tested across a known SpO2 using MCX software, and for the most part, we got error like around between plus or minus 3. But this is we need more data to calibrate it more, and actually we also this is a good start, because when we have the actual device, it's not as the MCX, because the LED emits around trillions photons or billions. I'm not really sure about the values, but it just shows like which is the best wavelength we can use for our case.
So for our abbreviated traceability matrix, our user needs were reliable SpO2 readings, real-time data processing, and small and lightweight. So for reliable SpO2 readings, we had our 3 wavelengths as our design input. We found those wavelengths to be 470, 550, and 590 nanometers as our design output. And then our design verification was using a code that converts the voltage to SpO2. For real-time data processing, we ideally wanted results displayed within 6 seconds on an OLED display, and we ended up finding that it could do it in roughly about 2 seconds. For small and lightweight, we wanted it to be over the finger at dimensions of 2 inches wide, 4 inches length, or width, length, and then less than 100 grams. For a 3D printed case, it ended up being smaller than that, but like we said, the electronics kind of overweight it more than we wanted it to. These are our roles and responsibilities and our Gantt chart and our PERT chart. We'd like to acknowledge our mentor, Dr. George Alexandrakis, for his guidance during this project. Also Justin Jaworski for providing components for the prototype, and then Dr. Gregory Turner for help with the circuit development.
So is Winter on that? That's a question.
So anyone has questions?
Any question from Winter? Or So, yeah, I do have a question.
Yep.
Have you worked with mentor consider patent? It is
I think someone actually not us, but in the beginning of the semester,
Yeah.
someone actually have solved this issue before, and that's why they refuse to help us
oh, okay.
because they didn't commercialize this yet, so we don't know what they're doing, and our device is not working yet.
Oh, not working yet.
Yeah,
Yet,
it's not.
yeah, that we need to still like calibrate it, and we
Uh-huh.
need to do a lot of things. I think it's gonna be a continuation part. It depends on the
I see.
department.
Yeah, but it's, I really like the quality.
Oh, thank you.
Good job. Thank you.
Real quick, this is Jeff. On the insertion of the finger, I guess in that hole, we'll say, is there a spring device or something to actually kind of squeeze around the finger? I wasn't able to see that.
There isn't a spring device. I was considering that with our original designs from last semester. There was a spring device. Regarding our prototype, this was just something that we needed to test with the. We just needed something to test, so I didn't really add a spring device in this. This came out like pretty abruptly, so.
So we just needed to put to align the wavelength
Yeah,
next to each other, and the
we just
detector.
needed something to align the wavelengths and the detectors within a certain distance between each other.
Okay. So do you have a concept on a wearable device?
Yes, we do have a
Real
concept.
snug to the finger.
Yes, we do. It's just
Okay.
on here.
All right.
Good deal. Thank you.
Thank you.
again. All right. Master group.